Chemistry is the study of matter and all its aspects. Why not study with us? Good day, everyone. Today, we will talk about heat capacity. So, about thermal energy, what's up with temperature versus heat? Temperature is related to the average kinetic energy of the particles in a substance. The SI unit for temperature is Kelvin. Kelvin is equals to Celsius plus 273 and Celsius is equals to Kelvin minus 273. Thermal energy is the total of all the kinetic and potential energy of all the particles in a substance. Examples of thermal energy are solar energy, melting ice, geothermal energy, heat energy in the ocean, rubbing your hand together, and burning candle. Thermal energy relationships. As temperature increases, so does thermal energy because the kinetic energy of the particles increase. If the temperature stays the same, the thermal energy in more massive substance is higher. Heat always flows from warmer to cooler objects. Specific heat, C, sometimes S, but usually C. Things heat up or cool down at different rates. Specific heat is the amount of heat required to raise the temperature of 1 kilogram, but in chemistry, we use grams of material by 1 degree C or K. They are the same size. C water is equals to 4,184 and C sand is equals to 664.
Sample specific heat capacity table. Specific heat capacities of some common substances. Every substance has its specific heat capacity in 1 joules per kilogram per degree Celsius. For the lead, 128 joules per kilogram per degree Celsius, gold 129 joules per kilogram per degree Celsius, mercury 138 joules per kilogram per degree Celsius, silver 234 joules per kilogram per degree Celsius, iron 448 joules per kilogram per degree Celsius, glass 837 joules per kilogram per degree Celsius, aluminum 899 joules per kilogram per degree Celsius, wood 1060 joules per kilogram per degree Celsius, ice 2090 joules per kilogram per degree Celsius, and water 4184 joules per kilogram per degree Celsius. And for the formula for heat capacity is Q is equal to M times change in time times Cp, wherein Q is the change in thermal energy, M is the substance, change in T is the change in temperature where you subtract the final time and the initial time, and Cp is the specific heat of a substance, and may lead to change in thermal energy is equal to mass of a substance multiplied to change in temperature and multiplied to the specific heat of a substance.
The specific heat of lead is 0.129 joules per gram per Celsius. Find the amount of heat released when 497 grams of lead are cooled from 37.2 degrees Celsius to 22.5 degrees Celsius. So, the given for this equation is we have M is the grams of the substance, which is 497 grams, and we have here the specific heat, which is 0.129 joules per gram per Celsius, and we have here the initial temperature, which is 37.2 degrees Celsius, and the final temperature, which is 22.5 degrees Celsius. The formula for this equation, right here, formula is delta T, or temperature change, equals to the final temperature minus the initial temperature. We have here Q, or heat release, is equals to M multiplied by specific heat times delta T, which is the temperature change. So we're first gonna solve for the temperature change. We have here delta T equals final temperature minus initial temperature. So we have 22.5 degrees Celsius minus 37.2 degrees Celsius. So if we're going to solve it with the use of our calculator, we now have negative 14.7 degrees Celsius. So we're going to solve for the next formula, which is Q equals M times specific heat times delta T. We're going to input the given, which is 497 grams times 0.129 joules per gram per Celsius, and delta T, which is negative 14.7 degrees Celsius that we solved earlier. So what we're going to do here now is we have to cancel the same units, degrees Celsius and the grams. And we have 497 times 0.129 joules times negative 14.7. So if we multiply this all, we have negative 942.46 joules. Or should we say negative 942.46 joules are released. When a 120 gram sample of aluminum absorbs 9,612 joules of heat, its temperature increases from 25 degrees Celsius to 115 degrees Celsius. Find the specific heat capacity of the aluminum. So we're going to write the given for this problem. We're going to write here given is M equals 120 grams, and heat released or absorbed rather is 9,612 joules. And the initial temperature is 25 degrees Celsius. For our final temperature, we have 115 degrees Celsius. So our formula here is just the same from earlier. We have delta T equals the final temperature minus initial temperature, and Q is equals to M times specific heat multiplied by temperature change. So the solution for this is we have to first solve for the temperature change, which is delta T equals the final temperature minus the initial temperature. So we have here 115 degrees Celsius minus 25 degrees Celsius. So when we're going to solve this with the use of our calculator, we have 90 degrees Celsius. For the next formula, we have Q equals M multiplied by specific heat times delta T that we solved earlier. Now we have 9,612 joules equals 120 grams times specific heat. Since we're searching for the specific heat, we're going to leave that there, and we're going to put 90 degrees Celsius here. So we're going to multiply both 120 grams and 90 degrees Celsius. We have here 9,612 joules. The product of 120 grams and 90 degrees Celsius is 10,800 grams degrees Celsius times specific heat. Since we're searching for specific heat, we have to cancel 10,800 grams degrees Celsius. And here. Going to cancel this out. Now we have specific heat, which is CS equals to 9,612 joules divided by 10,800 grams per degree Celsius, and we have here 0.89 joules per gram per degree Celsius. And this is the specific heat capacity of the aluminum. 4.82 grams of an unknown metal is heated to 115.0 degrees Celsius, then placed in a 35 ml of water at 28.7 degrees Celsius, which then heats up to 34.5 degrees Celsius. What is the specific heat of the metal? So the given here, we're going to write first the given for the unknown metal. Unknown metal. So we have here M is equals to 4.82 grams. And we have here the specific heat is unknown. And the final temperature is 115.0 degrees Celsius. So now we're going to write the given for the water, which is M is equals to 35 ml, or we can say that it is equals to 35 grams because it's just the same. Specific heat, which is 4.186 joules per gram per Celsius. And we have here the initial temperature, which is 28.7 degrees Celsius, and the final temperature, which is 34.5 degrees Celsius. So now that we are done writing down the given for the unknown metal and the water, we are now going to write down the solution for the heat of water. To write here heat of water, we're going to use the solution delta T equals the final temperature minus the initial temperature. So delta T equals 34.5 degrees Celsius minus 28.7 degrees Celsius. So when we're going to find the difference of these two, we now have 5.8 degrees Celsius. So now, we are going to solve for the heat absorbed by the water. So we have here heat absorbed by water. So we're going to use the solution Q is equals to M times CS times delta T. We have here Q is equals to 35 grams times 4.186 joules per gram per Celsius multiplied by 5.8 degrees Celsius. So what we're going to do here is we're going to cancel the same units, which is the grams and the degrees Celsius. So we now have Q is equals to 35 times 4.186 joules times 5.8. After that, we're going to solve for its product. We now have 849.758 joules, or should we say 850 joules. Note that this is the heat absorbed by the water, so this is also the heat released by the unknown metal. So now that we have solved for the heat absorbed by the water, we're going to put this aside for us to finally solve for the temperature change of the unknown metal. We're going to use delta T equals the final temperature minus the initial temperature. We have here 115.0 degrees Celsius minus 34.5 degrees Celsius. So, do note that this is the temperature of boiling water accumulated by subtracting the final temperature of metal to the final temperature of water. So now, we have delta T is equals to 80.5 degrees Celsius. So now that we have solved for the temperature difference between the water and the unknown metal, we now have to solve for the specific heat of the metal, which is we're going to use Q is equals to M times specific heat times delta T. We have here 850 joules from earlier. Is equals to 4.82 grams from the unknown metal times specific heat. Since we're solving for the specific heat, we're going to leave that there, and we have the delta T, which is 80.5 degrees Celsius. So now we're going to multiply 4.82 grams and 80.5 degrees Celsius. So we now have 850 joules equals 388.01 grams degree Celsius multiplied by specific heat. Since we're searching for specific heat, we now have to cancel 388.01 grams degrees Celsius. I'm going to write that here and here. 388.01 cancel out. So now we have specific heat 850 joules divided by 388.01 is equals to 2.19 joules per gram per degree Celsius. So that is the answer for the specific heat of the unknown metal.
So let's talk about heat transfer and changes of state. Thermal energy is the energy of a substance or system of terms of the motion or vibration of its molecules. The faster a molecules in a substance move, the more heat energy they have. You can transfer heat energy from one another. Heat transfer will occur when a hot object makes a contact to a colder one. When you add heat energy to a substance, two things may happen. Either the temperature of the substance will increase or the state of the substance will change. Also, we have three different ways to transfer. First is heat conduction. It is the transfer of energy from one molecule to another by a direct contact. Second, convection. It is the movement of heat by a fluid such as water or air. And radiation. It is the transfer of heat by electromagnetic waves. Heat can be transferred even if there is no change of state, or heat transfer can cause a change of state. It is true that heat may be transported without causing a change of state of the object. This occurs when heat is transferred in a solid material such as iron. It claims that it is unable to alter its state since melting a solid necessitates the breaking of cohesive connections between molecules in order for them to move about at equivalent kinetic energies. In brief, heat may be transmitted in a solid object without causing a change in it, and a high temperature is required to produce a change in state. For example, when you transfer heat in a 2.5 kilograms of iron for over 500 degrees Celsius, the temperature of the iron will change, but there is no change in the object state. We can determine this situation by using the provided formula. Q transferred is equals to C times the mass of the object times the change in temperature. The nature of the phase change depends on the direction of the heat transfer. Heat going into a substance changes it from solid to a liquid, and the changes of state involves energy at a constant temperature. This will occur if the object was liquid turns into solid, or what we call solidification or freezing. For example, an ice cube melts at a constant temperature. Why? The ice melts as a result of the latent heat of fusion. It is the quantity of heat necessary to change 1 gram of solid to a liquid with no temperature change, sometimes called the latent heat of fusion. That is why ice melts without an increase in temperature. And the equation for that is Q is equals to heat of fusion times the mass of the object.
Remember this, it's the heating or cooling curve for the water. Now in the science world, we use heating and cooling curves such to model physical changes. A heating or cooling curve is a simple line graph that shows a phase changes from a given substance that undergoes from a increasing or decreasing temperature. Now defining heating curves, notice that in general temperature goes up the longer the heating continues. However, there are two horizontal flat parts in the graph. This happens when there is a change of state. The plateaus are also called phase changes. First change of a state is melting. It is from solid to liquid. The temperature stays the same while a substance melts. And for the water, this temperature is 0 degrees Celsius because the melting point for the water is 0 degrees Celsius as well. Over the course of this line segment, both liquid and solid exist in various ratios, starting at 100% solid and ending at 100% liquid. The second change of state is a boiling, where from liquid to gas changes. The temperature stays the same while a substance boils. And for the water, this temperature is 100 degrees Celsius because the boiling point for water is 100 degrees Celsius as well. Over the course of this line segment, both liquid and gas exist in various ratios, starting at 100% liquid and ending at 100% gas. Now defining cooling curves, it is heating curves show how the temperature changes as a substance is heated up. Cooling curves are the opposite ones. They show how the temperature changes as a substance is cooled down. Just like heating curves, cooling curves have horizontal flat parts where the state changes from gas to liquid or from liquid to solid. These are mirror images of heating curves. Now, how does energy changes relates to this one? Now, since temperature is a measure of average kinetic energy, any change in temperature is a change in kinetic energy as well. All of diagonal line segments on heating or cooling curve show a temperature change and therefore in a change of kinetic energy as well. During these regions, a single state of matter exists and all the sample is either getting hotter or cooler. During the horizontal line segments, there is no change in temperature, so kinetic energy remains constant. However, all the energy that is absorbed or released is related to changes in potential energy. Just remember the 3 P's: plateau, phase change, and potential energy change. So let's look at this equation mass again. Q is equals to heat fusion times mass. There's also Q that equals to heat of vaporization times mass. And by the way, for when we are only talking about vaporization, why do we need this when I have Q transferred is equals to C times mass times change in temperature? Well, when a phase changes, there is no change in temperature, but there is definitely a change in energy.
So, if I want the total heat to take ice and turn it to steam, I need 3 steps. First step, to melt the ice, I need to multiply the heat of fusion with the mass. Second, then there is moving of the temperature from 0 degrees Celsius to 100 degrees Celsius. For this, there is a change in temperature, so we can use the amount of heat transferred is equal to the specific heat of the substance times mass of the substance times the change in temperature. But wait, that just takes us to 100 degrees Celsius. What about vaporizing the molecules? Well then, we need change in thermal energy is equals to the heat of vaporization times the mass of the substance. Then, add them all up and there it is. Now, lucky for us, just like there are tables for specific heats, there are also tables for heat of fusion and heat of vaporization. At least we don't have to worry about that. And now, let's take a look at it. Here we have heat of fusion of ice is equals to 333 joules per gram. Specific heat of water is equals to 4.2 joules per gram Kelvin. And heat of vaporization is equals to 2,260 joules per gram. Please remember and take note for this because we will use this in getting the total heat of energy to take ice and turn it to steam. How much heat is required to melt 500 grams of ice and heat the water to steam at 100 degrees Celsius? First, to melt ice, we will use the first step formula. Multiply the heat of fusion to its mass of the substance. Remember that the heat of fusion of ice is equal to 333 joules per gram. Now, let's input the values. Q is equal to 333 joules per gram times 500 grams of ice, and we get 1.67 times 10 to the power of 5 joules. Second, to raise water from 0 degrees Celsius to 100 degrees Celsius, we will use the second step formula. The amount of heat transferred is equal to the specific heat of the substance times the mass of the substance times the change in temperature. Remember that the specific heat of water is equal to 4.2 joules per gram Kelvin. Now, let's input the values. Q is equal to 4.2 joules per gram Kelvin times 500 grams of ice times, to get the change in temperature, we will subtract the final temperature to its initial temperature. And now, we get 2.1 times 10 to the power of 5 joules. To evaporate water at 100 degrees Celsius, we will use the third step formula. Change of thermal energy is equal to heat of vaporization times mass of the substance. Remember that the heat of vaporization is equal to 2,260 joules per gram. Now, let's input the values. Q is equal to 2,260 joules per gram times 500 grams of ice. And we get 1.13 times 10 to the power of 6 joules. Then, last, To get the total heat energy, we will add them all up. 1.67 times 10 to the power of 5 joule plus 2.1 times 10 to the power of 5 joule plus 1.13 times 10 to the power of 6 joule, we will get 1.51 times 10 to the power of 6 joule or 1510 kilojoule. So to convert it into kilojoule, let's divide it into 1000. 1,510,000 divided by 1000 is equals to 1510 kilojoule.
Calorimetry, aka how we measure heats of reaction. In a constant volume, or bomb calorimeter, we burn a combustible sample. From the heat change, we measure heat involved in a reaction to get the delta E for reaction. First, some heat from reaction warms the water, which we know the mass of, and C for heat of the water is equals to heat capacity multiplied to the water mass and multiplied by the delta T. Then, some heat from the reaction warms bomb, which has a known specific heat for the entire apparatus, so we don't need the mass. To get the heat of the bomb, we simply multiply the heat capacity and joules per Kelvin and multiply it to the delta T. To get the total heat involved, we simply add the heat of the water and heat of bomb. The main formula you will see in calorimeter is referred to as Q equals mCal, where Q is heat measured in either kilojoules or joules. M is the mass measured in grams. C or CS is the specific heat capacity. Its unit is joules per grams Celsius. And our delta T is the change of temperature, which is our final temperature minus our initial temperature, which is measured in Celsius. It is important to check that all of our given values are in these specific units before plugging your values into the formula.
As an example for a bomb calorimetry problem, a 0.5 gram sample of naphthalene is burned in a bomb calorimeter containing 650 grams of water at an initial temperature of 20 degrees Celsius. After the reaction, the final temperature of the water is 26.4 degrees Celsius. The heat capacity of the calorimeter is 420 joules per degree Celsius. Using this data, calculate the heat of combustion of naphthalene in kilojoules. To solve this problem, we need to first identify the given. For the naphthalene and bomb calorimeter, we have the given mass of 0.5 grams and the specific heat capacity of calorimeter, which is 420 joules per degree Celsius. And for the water, we have the given mass of 650 milliliters, that is also equivalent to 650 grams, and the given specific heat capacity of water, which can be googled and searched, that equals to 4.184 joules per grams degree Celsius, the initial temperature of 20 degrees Celsius, and the final temperature of 26.4 degrees Celsius. The second step to solve this problem is to identify the formula that we're going to use. We have the first formula, which is the heat transfer, where Q is equals to the mass times the specific heat capacity times the change in temperature. To find the change in temperature, we have change in temperature is equals to the final temperature minus the initial temperature. And to find the heat transfer of the bomb, we have Q is equal to the bomb heat capacity times the change in temperature. The next step we're going to do
is to solve for the change in temperature. The change in temperature can be accumulated by subtracting the final temperature to the initial temperature. By substituting the given values, we have 26.4 degrees Celsius minus 20 degrees Celsius, and that will going to give us a 6.4 degrees Celsius change in temperature. After we found the change in temperature, we can now use the formula of heat transfer to the water. We need to substitute the given values, that is, Q is equal to 650 grams, which is the grams or mass of water, times 4.184 joules per grams degrees Celsius, or the specific heat capacity of water, times 6.4 degrees Celsius, or the change in temperature. By multiplying this given, we will get 17,405.44 joules. Now that we've found the heat transfer reaction to water, we need next to solve for the heat transferred from reaction to bomb. We need to use the formula Q is equals to bomb heat capacity times the change in temperature. As what was written in the given, we have 420 joules per degree Celsius, which is the bomb heat capacity, and the change in temperature of 6.4 degrees Celsius. By multiplying these values, we can cancel out the degrees Celsius, and that will give us 2,688 joules. Lastly, to solve for the total heat evolved, we just simply add the heat transferred reaction to water and the heat transferred from reaction to the bomb. By substituting these values, we will get 17,405.44 joules plus 2,688 joules is equal to 20,093.44 joules. It was stated in the problem that we need to have a result that is in kilojoules unit. So to get this result, we just simply divide the 20,093.44 joules to 1,000 joules, and that will going to give us 20.093 kilojoules. And that is now the value or the total heat evolved of 0.5 grams of naphthalene.
For our last example, we have if I burn 0.315 moles of hexane or C6H14 in a bomb calorimeter containing 5.65 liters of water, what's the molar heat of combustion of hexane if the water temperature rises 55.4 degrees Celsius? The heat capacity of water is 4.184 joules per grams per degree Celsius. Let's put all the given first. We have 5.65 liters converted to grams. We have 5,650 grams of H2O. We also have 4.184 joules per grams per degree Celsius and 55.4 degrees Celsius. The heat of combustion is calculated by multiplying the mass of the water times the specific heat of the water times the change in temperature, or we have heat of combustion is equal to mass times specific heat times change in temperature. Then heat of combustion is equal to 5,650 grams of H2O times 4.184 joules per grams per degree Celsius times 55.4 degrees Celsius. We have 1,309,633.845 joules. The typical molar heat of combustion is given as kilojoules per mole. That's why we need to convert joules to kilojoules for us to find the molar heat of combustion of the hexane. 1,309,633.845 joules converted to kilojoules will be 1,310 kilojoules. The question is, do you think we're done? No, because we were asked for the molar heat of combustion. Molar heat of combustion versus heat of combustion. Molar heat of combustion is the amount of energy released in burning completely 1 mole of substance, versus heat of combustion, it is the amount of heat released per unit mass or unit volume of a substance when the substance is completely burned. We also have heat of fusion versus molar heat of fusion, and heat of vaporization versus molar heat of vaporization, so be watchful. What we calculated is the amount of energy generated when 0.315 moles of hexane is burned, which is close but not quite what we were asked for. To find the molar heat of combustion, we need to multiply this by 1 mole over 0.315 moles, or we have molar heat of combustion is equal to 1,310 kilojoules multiplied by the answer of 1 mole over 0.315 moles, equal to molar heat of combustion 1,310 kilojoules times 3.17 moles. As a result, the molar heat of combustion of hexane is 4,153 kilojoules per mole.